Matrices are a great way to organize and manipulate and gain insight out of data. And in particular, matrices are useful for data that involves some kind of relationship or association or the like. So it's some things we might not have even thought of. And matrices are very powerful ways to handle that. So a matrix is just an array of numbers. And I want to do something a little bit more colorful to see why some things naturally fall into an array. So let's look at the relationship between animals and body parts. So, for example, animals and stomachs, or animals and legs, or animals and whiskers, or whatever. And we'll just keep it simple. And the idea is different kinds of animals have a different number of stomachs. So you might naturally arrange those numbers into a list. And they have different numbers of legs. So again, you might naturally arrange those numbers into a list. And now we've got two lists of animal body part relationships. And that's just very naturally a matrix. So my chosen animals are cows, ducks, and spiders. So we've got animals. And cow, duck, spider, those are my animals. And my chosen body parts are stomachs and legs. So that's the situation. And we're going to have to call on a little bit of outside knowledge to fill in the values of this matrix. So far I've just said, okay, yeah, there's going to be some stuff. And but a good computer scientist is interested in everything. So if I say something that doesn't make sense to you, look it up. I'm trying to say the right thing. So let's think about stomachs. A cow has 4. So in the spot corresponding to stomachs and cows, I put a number 4, just the number. I might need to think about there being units or something on that, but for the moment, I just put the number. And a duck has 1, and a spider doesn't have a stomach at all. So there's my stomach line. And if you think about legs, then a cow has 4, and a duck has 2. We don't have to go into the technicalities about whether a wing is a leg or a leg is a wing. One's white meat, one's dark meat, okay? And spiders have 8. And so what we have here is an array that has 2 rows and 3 columns, and that's a matrix. And it represents the relationship between body parts and animals. So anyway, so the traditional notation for a matrix is to enclose it in square brackets, and that works out pretty well. And this is a 2 by 3 matrix. So we write that as 2 times 3, but it's not, it's by, it's not a multiplication. Oh wait, it is a multiplication. There are 6 entries here. So this is kind of an overloaded operator, this X symbol, but this is a 2 by 3 matrix. And so that's 2 rows and 3 columns. And just for a little bit of practice, the entry in row 2, column 3 is that's the 2, 3 entry. So it's always row then column. And in this case, if we look at row 2 and column 3, then the entry there is 8. So if you call the matrix, let's pick a good symbol for the matrix, M, then usually we use a big letter for matrices and a little letter for the entries. So if I have some matrix capital M, the entries are little m sub ij, and I is the row, J is the column. And so in this case, we're saying that M23 is 8, and I'll do one more just for fun. M12 is 1. So M12 is first row, second column. There we go. So now we've got this data about this relationship encoded in a matrix. Let me give you another example, which is just super, super, super useful. And I'm going to look into a mythical town, and the town has a Starbucks and a McDonald's and a gas station and a grocery store. I think that's what it was going to be. No, it has cleaners and a grocery store. Yeah, it's a nice, clean town. So, so let's see what we can say about this. And the town, the roads are kind of not as well organized as they might have been, because they might have not been organized at all. They might have just come together in some kind of almost random pattern. But let's imagine this is a very stylized map of this little town. And I've got Starbucks, and I've got the cleaners, and I've got the grocery, and I have McDonald's. I'm not saying that we have to like these things. I'm just saying that we might have noticed that we have these things. And what I've done is I've drawn a little stylized map. So I'm not showing the roads or the composition of the roads or the amount of traffic on the roads or whatever. I'm just saying there is a good way to get from Starbucks to the cleaners, and there is a good way to get from Starbucks to McDonald's, and so forth and so on. So these are the paths that exist in this little town. So we can encode those paths in a matrix. So we'll call that matrix of connections. That's not the technical term. The technical term is an adjacency matrix. So what's gone on here in the first case, the relationship between the two things was a relationship of belonging to. The stomach belongs to the cow, or the stomach belongs to the duck, or the legs belong to the spider. And here the relationship is just whether you're connected to. But you can represent this in a matrix quite easily and quite nicely. And so this is called an adjacency matrix. And let's see if we can do this in alphabetical order. So I'll have one column for each of the establishments in this town, and one row for each of the establishments. And I'm going to put a 0 if there's no direct route from one to the other, and a 1 if there is a direct route. So we've got CGMS, CGMS in the same order. And so now if we start to look, if we start, I guess I put C in the first row. So from the cleaners, I'm going to just say, hey, we can get from the cleaners to itself. There might be conventions in which that might not be the case, but that would be a different kind of situation. Anyway, we can get from the cleaners to Starbucks or to the groceries or to the cleaners itself. So I'm going to make that line. We can go from cleaner to cleaner, cleaner to grocery, not from cleaner to McDonald's, and yes, from cleaner to Starbucks. So this is just a kind of a binary thing. There are other situations in which it might not be binary, but this one's binary. And I'm just going to fill in the rest. If I look at the grocers, I can get to the grocers, of course, and I can get to the cleaners, and I can get to McDonald's. So I have 1 for the cleaners, 1 for the grocers, 1 for McDonald's, and 0 for Starbucks. There's no direct path from the grocer to Starbucks. And that's what this 0 means. Anyway, to keep filling in, I'm going to put some more colors in just to make it fun. McDonald's, we can get to Starbucks or the grocery, but not to the cleaners. And from Starbucks, we can get to the cleaners and McDonald's, but not to the grocery. So there's the data. This array of numbers encodes this situation, and we can think about that as a matrix. So there it is. So there's the adjacency matrix for this little map. The word we're searching for here is graph, but that's what comes next. That's why we're doing matrices, is so we can work with graphs. It's not the only reason, but so we can. Okay. So a matrix is a way of organizing data. There's a little bit of vocabulary about it as far as the 2-3 entry is row 2, column 3, and that's about what we need to do. So you can imagine this is some big database of animals and body parts, and I'm not quite sure where to go with that, so let's just move on. Now, so this is just storing the data. This is just a way to organize the data so that we can store it. So how are we going to use it? And I want to illustrate one use now, and then there'll be other uses later. So this is the first one to get us started. And so here's the deal. I'm going to make up a story. Noah's crazy cousin didn't like this 2x2 business for the ark. So you know about Noah's Ark, but no one ever talks about his cousin because he was a little, mashugana. So Noah's cousin says, I'm going to have different numbers of animals. So I'm not sure I want to write this down, but I guess I'll do it. So Noah's cousin, and we're not going to look at all the animals. We're going to look at cows, ducks, and spiders. And Noah's cousin has, sorry, I'm going to look at my notes to make sure I get the arithmetic to work out the way I did it. Okay, Noah's cousin has 4 cows. So that sounds like a good deal to me. So he has 4 cows, and he's got 8 ducks, and whether he likes it or not, he's got 3 spiders. So that's a different kind of data. That's not a relationship of any kind. That's just a count. I've got so and so many. I mean, it's like going through the grocery store and they're counting cans of tuna and boxes of spaghetti and macaroni and cheeses and apples, right? So this is just a count. Not much structure to that data other than something you might impose, like I want to have it in alphabetical order, or the order that I would go through the store or something like that. But that's a different matter. All we have right now is 4 cows, 8 ducks, and 3 spiders. How many stomachs do we have? How many legs do we have? And now that is combining the number of animals data with the matrix that encodes the relationship between the body parts and the animals. And so this is a pretty natural situation. You can imagine some kind of inventory thing, and you've got how many of these you have and how many whatever property those things might have. And so this is not a bizarre situation, although, Noah's cousin. Anyway, there's a way that we can handle all this. So if we ask about stomachs, so now we're actually doing arithmetic. We're counting stomachs, and I've got I'm going to color code this. I've got 4 cows, 8 ducks, and 3 spiders. So that's in green, and now I'm going to throw in red the number of body parts. Well, the cows have 4 stomachs, and the ducks have 1 stomach, and the spiders have 0 stomachs. So now I've got the situation of that's how many cow stomachs I have, how many duck stomachs I have, and how many spider stomachs I have. Of course, I never have spider stomachs, but that's the way it goes. And then I'm going to add those up. So for stomachs, I've got 4 times 4 plus 8 times 1 plus 3. So I have 16 plus 8 is 24 stomachs. If you can stomach the smell from all these animals, then that's pretty good. Okay. And then we were going to ask about legs, and I'm going to do legs the same way. and because I'm thinking about how this data is organized, I'm not writing it down in the order that I'm going to calculate it. I'm organizing this calculation. So we still have the same number of cows, ducks, and spiders. So that's going to be color-coded to be the same kind of thing. So 483. And then as far as number of legs they have, well, the cow has 4, and the ducks have 2, and the spiders have 8. And so we could say how many cow legs we have, how many duck legs we have, and how many spider legs we have. And then, we better add those up. So we add those up, and we come up with 16 plus 16 is 32 plus 24 is 56, I believe. So we have 24 stomachs and 56 legs. Make of that what you will. Okay. Now the thing is, and you can see from how I've organized this, or you color-coded it, is that you have the same data appearing as the first factor in each term, 483, 483. And so there's a repeated calculation here. And so there's a way to encode this repeated calculation involving the matrix. So the matrix we had was, and usually when you're reading a matrix out loud, you read it row by row in the normal English order. Even if you don't speak English, you read it row by row in the normal English order. So the matrix that we had, the relationship matrix, was 410. That was the first row. Second row was 428. And the way we represent this calculation is by putting the animal data, the animal count data, into a matrix, and that's only got one dimension, right? I mean, but that's written as a column, and that animal data is 483. So I've got the relationship data, I've got the animal data, and this operation gives us the body part data. So to get the stomachs, well, we know what's going to happen. I'm going to write this. I'm going to write the answer and then explain what happened here. This is 24 and 56. So this is a graphical representation of these calculations up here. So I've got 410, and then the convention is you take the row on the left and you multiply term by term by the column on the right and add those up. And so that's exactly what happened here. And then you take the row on the left and term by term, the column on the right, multiply them term by term and add those up. And that's exactly what happened here. And the conclusion we drew was that there were this many stomachs and this many legs. So this is called matrix multiplication. And the idea is, and there has to be a matchup here, right? I've got 3 kinds of animals, so I better have 3 kinds of animals. And so that would have to match up. If I had a 4th kind of animal, I wouldn't have any data about it, and it wouldn't make any sense to try to calculate this 4th kind of animal because I don't have any data about how many stomachs it has. So the dimensions have to match up. This is a 2 by 3, this is a 3 by 1, and we end up with a 2 by 1, and that's the general rule. And we do this matrix multiplication. The matrix multiplication is up here. This is the calculation. This is the way we write it down and encode it. And it's an extremely useful operation in many, many, many applications and many, many, many calculations. What blows my mind after 50 years is that the C language did not include matrices. Later variants include matrices. Almost every higher order language includes matrices. They call them arrays, but they're matrices. And there are a lot of languages where if you get the types right, if you're object oriented and you have a matrix as like a class and a matrix as a class, you can just write m times n as a program instruction, and that's built in. And so this is not a trivial matter. It is something that's very important in applications, and it's something that we're going to use a lot, well, for the rest of our lives.